All right. Hey, everyone. My name is Burek. I guess it's about time to start, so we'll start. Today I'm going to be talking about the automated performance testing of Postgres. This is an engineering tool that I've been developing at Heroku, and hope to share it all with you and see if it can be useful outside of our own little corner of the world. First things first, what is Heroku? Heroku is a platform as a service. It's a company where you can give us your application code and we will run it for you on AWS and give you a really easy way of scaling up, creating many dynos or LXC containers that run different types of processes, and scale up, scale down, have application restarting, monitoring, health checks, routing to the various dynos wherever they are, a lot of things. We are a company that tries to make it, take the server administration out of running a website or a web business or even an API. Heroku Postgres, on the other hand, is the other part of that. Part of what Heroku does is forces you to really rethink your application in terms of stateless processes. If you have a LXC container that has application code in it, it can go away at any time. That's just the realistic part of being in a not the most dependable infrastructure. Part of that is you have to put your state somewhere. So we provide Heroku Postgres as a service for you to be able to have a place where your application state, your data, is able to live and persist beyond the lifetime of individual chunks of your application. So we are a very large provider of Postgres. We run now almost 1 million databases across our service. We do that over several thousand servers. We monitor and maintain them basically 24 hours a day as long as you need them or want them. We also have a lot of breadth in the types of services that we offer. So you can get a free database that has a set number of rows that are available to it, that is running on a very highly concurrent server with many other databases, all the way up to a massive, the biggest instance that Amazon sells. We will give you that for the entire thing to bend to your will and be able to use it as you see fit. So we are also doing this as a service, really. We're not a hardware seller. So we are also concerned in monitoring Postgres, monitoring the underlying OS instance, making sure that it's healthy, making sure that it doesn't lock up, making sure that it doesn't drop off the planet, which happens frequently in a cloud environment. So we also do a lot of things with continuous archiving of WAL. When you create a database, we set that up to be continuously persisting to an object store that's highly available and very reliable, so that we're able to take that write-ahead log and then do things like create hot standby followers, or creating point-in-time recoveries of something that we call a fork. So we can do a lot of these things that are around Postgres, and we are really concerned about taking what you can do with Postgres and building up around it. And it's been an interesting business to try and develop and try to do things that web developers and other businesses want to do things around Postgres. So Heroku Postgres is fairly separate from Heroku. We're still in the same company, and we eat lunch together, and we work with our colleagues, but we are running our own infrastructure. We manage instances in AWS that are completely different from the rest of Heroku. We have our own orchestration framework and systems. We have our own monitoring. We have our own health checks, and the way that we deal with these servers is very different from Heroku in the application execution environment. We're 100% backed by EBS block storage, elastic block storage within Amazon. This is something that we made a choice with very early on because of how failure prone the cloud can be. We want to give you the best possible chance of having your data survive. because that's really what's important to us and our customers, that your data continues to persist and keep on going. So we have this as kind of a not necessarily limitation, but a fundamental assumption of what we build our infrastructure on. So being upfront about that. We do have a mutable-ish infrastructure. When we launch a server, it is there and it's going to run, and we're not going to touch it as much as possible. Part of this is because of how difficult it is to deal with change management and the various change management agents. It's something also that if we have something that is working, then don't want to touch it. We don't want to cause downtime for a customer because we're trying to update something that they don't actually need. We say immutable-ish, though, because things happen. You have to upgrade OpenSSL. There are things that we have to upgrade Postgres on the instance for, so it's immutable-ish. I wish it was more immutable than it actually is, but that's how it goes. Our servers are long running. I actually was involved in an incident a few weeks ago where we killed a server that had an uptime of over 900 days, and in Amazon Web Services, that is rare. Things can, in a very elastic environment such as ours, long-running servers are something of a rarity, but we have to be able to work with that. And that kind of comes down to then, if we are pushing an improvement or something out to production, we want to make sure that it is functional and that it works, and that if it continues to work, we're not going to touch it. We're not going to try and break this thing that is out there. The problem is that we have to make sure that it does work first. So we have actually a lot of continuous integration testing around checking to make sure that new instances are giving databases that are accessible, making sure that the streaming write-ahead log is downloading from the object store and being restored. We have this sort of continuous regression testing against our API, but this is not something that is really around Postgres. It's more about, is Postgres running and is it accessible, not necessarily about how it's working or the more fine-grained things of how well it's working. So something that I've been working on and we've been moving to now is sort of a continuous regression testing platform, or something that is running in Heroku that we're able to check and confirm that we are, in fact, making our customers, giving our customers better instances, and we're not inadvertently regressing how Postgres performs. So that's something that we've been calling PGPerf. Just it's easier to type PGPerf than Postgres-performance. And when you're doing that a few times a day, it saves some time. So with that sort of background, I did want to talk a little bit about how benchmarking in general is in the Postgres world. This is all something that that is a little bit foreign to me. I'm more of a systems administrator and have been working with Postgres for only a few years. So we've been working with various people within the community and also various people within Heroku to understand this better and find a way to have a good sort of baseline to work on and start to improve things. So PGBench is really one of the more understood and widely used tools. It is included in Postgres, and it is fairly venerable. PGBench Tools by Greg Smith is a suite of code that enables you to take the PGBench and run many tests. Perhaps you want to run many different scales or many different client sets and then have them be written to a database so you can analyze them and build up a web report. This is a really great tool for tying together the things that PGBench does individually very well and then make a more actionable and complete picture of what your database is actually capable of in different ways. What we've done is we've actually taken PGBench and tools and forked it into PGBench Collector. This is something that Peter Gagan, another employee that is at Heroku, he has been working with this to make it more web app friendly, make it something that we can start to have maybe less data that is being taken. So we're taking data and then we're downsampling it in a relatively understood way so that we don't actually overload our testing database while we're testing a target database. So this is also on GitHub and open source and available. So if you please take a look, we're eager to have some improvements and other eyes on this project. So one part of this that is a point of contention and makes benchmarking a little bit more controversial than you would think is that believable benchmarking is hard. It is extremely easy to make trivial benchmarks or trivial changes that are to illustrate a point. So if you come with a preconceived notion of what this should be, it's easy to bend benchmarking to prove what you expect to be seen. So something that I've been trying to do is limit what we do in benchmarking to something that is fairly scientific and measured. Like we're only testing testable single hypotheses instead of just doing things like shootouts or trying to get buying advice. And we're not really looking to manipulate the idea of us through this benchmark tool. And honestly, as an engineer, this is super helpful. It has exposed some things that we're working to improve. So in that way, I believe that's helpful. But you have to be able to really take the unvarnished truth to see what the problems are, and how to get past them. So it's an engineering tool. That's really the thrust of this. So another thing that we do is also want to do a gut check, see how bad things are. Do we need to go back and take a second look at the configurations, or the systems, or the builds of Postgres that we're using? So then the question now becomes, how do we run PGBench Collector flexibly and continuously with no servers? Well, we're kind of lucky because we are on Heroku, and we have a platform as a service to be able to work with. So that's where PGPerf comes in. This application is running on Heroku, and we have it tied into our production systems so that we're able to create new databases, submit them to PGPerf, and have them run benchmarks. You can see here, this is an output of the processes that we're currently running for PGPerf. We run several workers and web front ends for an API, and then have these processes here that actually host PGBench tools and PGBench Collector in a way of trying to make this more isolated and make it more possible to have a benchmark that we can at least use. So PXDinos is the big kind of game changer here. In this view, you can kind of see this is a PX, whereas these are 1X. 1X dinos are 512 megabyte LXC containers. They're on instances that are shared with other things. They could be doing anything in there. They could be doing Bitcoin mining, or just idling, or sleep 100, or just running in a loop. So running benchmarks on shared infrastructure, a little harder than we would like it to be. So PXDinos give us the ability to still use Heroku and the tools that we have available, but run it on full C1 extra large instances in a way that it provides a lot more isolation. So yeah, it's really, if you don't have isolation for your testing platform and for the database that you're running against, then good luck trying to figure out what's going on. Noisy neighbors and crosstalk is a huge problem with getting believable results like this. So what we are doing is we are compiling Postgres and injecting PGBench into the dyno when we deploy the application. This sort of approach then gives us the ability to have an application that's written into a higher level language. In this case, we use Ruby and then the Sidekick worker pattern. And we're able to now use Ruby to control PGBench and the PGBench tools, which is written in Bash, in a more flexible way. Sidekick also gives us a way of viewing the work that is undergoing at this point. This is extremely hard to read, I apologize. But this does show these 5 workers working on benchmarks when the screenshot was taken. So this gives us a lot of extra things, and I'm free to kind of more focus on the actual benchmarking and the improvements that we're building in. So how do we use this? It's actually a really simple flag here. We just put, if you're a Heroku employee for right now, you can put in the -- benchmark and then have a description that is linked to the server and then submitted to PGPerf so that they can be run the full suite of benchmarks on it. When it's submitted to PGPerf, it's required to give the administrator credentials, so you can do a checkpoint and clear the buffers for PGBench, and as well as the owner, email, what it actually denotes, like what your description is, and just try to get some more metadata around what you're running. So for this, we have something that is getting that is able to get long-running benchmarks and historical benchmarks while we are also doing other things as well. So that's more about PGPerf. One last thing about the architecture is that the PXDinos that we run, they're detached from Heroku, from the process management. So they will run for 24 hours or until they're killed by Sidekick. So that allows us to continue to develop on the application and not have to restart any jobs that are running when we update it. So general things. Now, limitations. What we're doing here is something that is pretty highly focused. There's no real front end. The front end that we've been working with is actually the data clips that is also provided with Heroku production databases. So we have access to the data, but it's a lot of SQL. We're able to take this data and then export it into Postgres or other tools or Google Charts and graph it that way, but it's not perfect. There are limitations here with the job runners itself. The overlapping tests are a problem. You don't want to run a select PGBench test at the same time that running TCP/B because they will pollute and have really bad noisy neighbor problems. So we only do one job for the entire suite. The PGBench Collector runs all of the progression of clients and the scale of PGBench in one job. This does limit the job to 24 hours because the dyno restarts every 24 hours. So that is a limitation. What I'm going to be showing you today is some results that are working on 10-minute tests per client. So that's limited, but it's something I want to be upfront about. Also, the C1X large dyno, it is a discrete power. It's fairly limited. So the higher level of tests where we have many clients, we want to take a closer look at that and see if that pays off or is believable itself. The other thing with this is that there's no SSH access, so no system data as PGBench Tools is trying to provide as well. So what I'm going to be running, showing you today is TCP Be SQL and Select SQL results and with a PGBench scale that translates to about 10 gigabytes of data. This is something that reflects our current best use case. If you are running an app in Heroku, we recommend that your hot data set fits in memory. That's not always the easiest thing to do, and it is a limitation that we recognize. But our experience has been that it really is a powerful way for you to get the most out of your database with reliable performance and repeatable queries and returns. So, I mean, something that we've seen though with this test is that one bottleneck is always covering up another bottleneck. So it's a process of iteratively working through these different things as we find them. All right, so the system setup that I'm going to be showing today, we have systems that are running all the same version of Ubuntu Linux, and we are showing 3 instance sizes that correspond to 3 different plans that we have, Ika, Baku, and Mecca. They correspond to large instances, 2x large instances, and 4 extra large instances. This is the kind of range that we're looking at right now. These instances are then set up with a elastic block storage root, so it survives a reboot, a separate disk for the write-ahead log, and a separate disk for the database. That allows us for, if one of these disks fails, we actually are able to preserve your data and get your database back. So this is the outlines of the instances. So the first instance comparison that we did was instance size. This is a pretty kind of a no-brainer test. What we're doing is testing previous generation M1, M2 instances with R3 instances, which is the high memory. And we can see pretty plainly that legacy Baku is the green line, and legacy Mecca is the blue line here, and the more up-to-date R3 instances are much better. In some cases, the Baku is even better than our previous top-of-the-line generation Mecca before. So what we're seeing here is purely just instance size. So that the disks are the same, the OS is the same, the build of Postgres is the same, the data size is the same. So we're testing the network I/O, the memory I/O, and also in this case, I think the memory size. But if your hot data set is already in memory, you would not really expect a doubling of the RAM to be that much of an improvement. So we're seeing this in this case. Yes?
Can you tell us what the axes are on that? I can't read it.
I apologize. This is average transactions per second and then number of clients. So again, the breadth of tests that we're looking at is, does it get worse or better as the clients go up? And average transactions per second is our main measure at this point. So with the TCP Be Test is something that this is actually a little bit of a surprise to us. When we're testing the write-heavy traffic, we are getting better performance with the newer instances, but at around 160 clients, we're actually getting a degradation in performance. And this is something that we started to look at with when we actually were able to find that this is actually dependent on the new type of EBS volumes that Amazon provides. And that is actually the wall disk that we're working on. So after this test, we went back and took a look at the performance of if you vary the type of EBS for the wall disk. And that seemed to be, actually was a pretty big impact for that TCP/Be test. Select test, same thing. They're about equal or comparable performance between each of these generations excuse me. These are sharing the same instance types and then just varying the wall disk. For the GP2 wall disk, that's actually a bursting SSD-based wall disk. And the bursting is really showing in this case. So for here, these two lines of data are the baseline Baku and the baseline Mecca. And as soon as we add these GP2 EBS disks for the wall, suddenly we get a huge burst in the transactions per second that are available on the lower end of the spectrum. However, at the higher end of the spectrum, we start to decay. So that then begs the question, what's happening? So honestly, in this case, SSDs are not really SSD-backed EBS, which is an important thing to note. It turns out that the GP2 EBS block size, block devices, these are things that burst. So you can get up to about 3,000 IOPS of data throughput at the very beginning when you first start to use them. After about 30 minutes for the volume size that we're working with, it decays down to around about 200 IOPS. So that is actually what we're seeing here. Our idea that maybe that a burstable, slightly faster than normal EBS disk would be helpful in all cases doesn't hold up. So this is something that we're now working with to find a better size and sort of specifications of these wall disks to be able to handle more write traffic. also, it also shows kind of the shortcomings of the PGPerf tests, where each one of these is about 10 minutes. Getting up to about this point, you've exhausted the 30,000 IOPS kind of bursting of that disk. So then we see that in the rest of the chart. All right. So yes, we have more bottlenecks that show up. That the wall disk, if we improve it, that is going to improve the write performance of our databases, but it comes at a cost when we use disks that are not always going to be giving us the same performance. So the final thing that I did want to show is something around the EBS type of the database disk. Again, with the select test, we're testing mostly in-memory systems. It's not going to the disk, and the results between each one of these sets are really comparable. The other part of this is then getting back into, we actually are wall limited for most of these write things. So creating the PRIOPS disk, or going to PRIOPS disks, gives us a way of giving reliable read performance, but the write performance is still going to be bottlenecked on the wall disk. So this is something that we are taking to heart and working to improve on our systems. Question?
Have you looked at how the performance changes if you turn off synchronous commits and play with commit siblings and whatnot?
No, we haven't. And that's something that would be scary. Because in a system that can have things fail, we would want to have the best chance of the data making it off the system. But
I mean, you're losing what, 10 or 20 milliseconds potentially.
Potentially, yeah. So yeah, and that's an improvement that I think that we can test with this.
Yeah, because I would imagine your F-sync times are just really high when you're trying to do that sort of thing.
Right. And this is network attached storage. So if you're dealing with an iSCSI interface or SAN or EBS, there are similar, not exactly the same, but similar techniques at hand. All right. So one thing that we've been really excited to try and do here is try to make this available for testing of the point releases of Postgres. The various versions of Postgres that we work with right now are the latest that's in production is 9.3.5, and that's what we've been dealing with when developing this. But as we move on to the newer versions of Postgres with 9.4 and 9.3.6, I'm really like to see how these sort of simplistic tests either change or don't change or modify what our bottlenecks are. So that's something that we're looking forward to. As I mentioned before, we would really like to be splitting up the tests into tuples of the type of script that we're running, the number of clients, and then the scale of PGBench that we're working with, so that we can do longer and better tests. I mean, the data that I've been showing today is not very quiet. It can go up and down and it puts some doubt into exactly what we're looking at and how we interpret it. So this is an improvement that we definitely want to make. Another thing of this PGPerf, we are actually looking at using it to stress test, heavily writing a lot of data into Postgres. And that's something that we've seen with bugs in either LVM or XFS kernels in the past. We would like to be able to test that as we go to newer versions of OSs or even newer kernels, to be able to have as much write traffic coming to this as possible and simulate a potentially very aggressive environment where we have seen some of these failures in the past. Another thing that we definitely want to work is a little bit less manual administration, less reliance on the data clips and sort of getting the reports and charts out, and potentially getting a user interface. Then also we want to try to add auto-scaling of the PXDinos. So if you would like to run PGPerf, then you'd be able to work with it and not have to have a PXDino running all the time. final thing that I would like to extend this project to do is have burn-in of production instances. Something that we've heard about in Amazon Web Services is not all instances are born equal. We would like to really test that and find out if that's the case and begin to qualify and burn in things as we bring them into service and be able to give our customers basically the best experience possible. So these are all things that are on the table for PGPerf, and we're going to be working on them for over the next couple weeks and a couple months. One thing, though, that has been really kind of come out of this PGBench stuff is there are things that we could do better there. The lack of histograms that I've not been able to see within PGBench makes it a little limiting to understand exactly what we're dealing with. There are things that we've been seeing in the system community and other parts of the computing industry that are using flame graphs and other sort of histogram and display techniques to show kind of what is happening at a really low performance level. So that's something that we would really like to see. I guess I would like to see and try to work with. Also, that goes with latency and getting 90th, 9th, and 90th percentiles. But these are all things that I would like, and we would like to try and see how we could get them done. So that is pretty much what I had came to present. The PGPerf is something that we are actually now releasing to the world. This is something that I actually can't pull up. But if you go to github.com/Heroku/PGPerf, it's actually now open source under an MIT license so that other people can start to look at how we are trying to qualify and move forward with the performance of our Postgres instances, and just try and give us feedback and start to improve the tool. So, thank you. Question? So the question is, are there plans to make it easier to run this on non-AWS or on bare metal hardware? It's technically possible now. So the application itself, if you were to run, say, DS or a Docker-based system, you could spin up the PGBench tools worker and have it run on hardware, pass it in the super user credentials of whatever you're benchmarking, and then be able to let it tear loose on what your target is. So it's possible. We try to make it as easy to use on Heroku as possible, but also as decoupled as possible. Makes sense?
As a customer, it would be nice to see, with my data, my kind of sites that I have in mind, for you to do stress testing with that kind of preemptively,
right?
So that I can know exactly what to buy. Is that something, is that a far future feature? Or is that realistic?
It's something that is difficult. So the actual use case of what your data is and what your workload is hard to map to a synthetic benchmark. So it's something that I think we would like to start to show that for certain configurations and certain assumptions that certain things are doing either improving or maybe not the best choice. But I mean that's something that we can work with as we build this from an engineering tool to a more widely applicable tool to guide your process. Does that make sense?
When I was managing databases on bare iron, when I would get a new machine in, I would start with a Bonnie++ benchmark and a street benchmark before I loaded the database on and started benchmarking the database. Have you done any of that on these machines on Amazon?
No, we haven't, because the issue is we would like to. especially because of what we've heard of the not instances are born equal and variability that is there. The thing, though, that we kind of limited our scope to is we're a Postgres shop, and we're super interested about how Postgres is actually working on these things. So as we've seen, we've already discovered bottlenecks within our configuration that we're able to change. So we're starting to work in that direction, though, where hopefully we will be then running up against benchmark or bottlenecks that can be uncovered by those sorts of benchmarks. Make sense?
Yeah, I always find it easier to interpret the database benchmarks with those underlying numbers.
All right, that's fair. Any other questions? All right, well, thank you very much.